Welcome to this lecture on plasmonic hotspots and metallic nanostructures. Today we will explore one of the most fascinating phenomena in nanophotonics, regions where electromagnetic fields are enhanced by orders of magnitude. Let's start with a fundamental question. What exactly are plasmonic hotspots? Plasmonic hotspots are nanoscale regions where the electromagnetic field intensity can be amplified by factors ranging from 10,000 to 100 million times compared to the incident field. These extraordinary enhancements arise from collective oscillations of conduction electrons in metallic nanostructures, which we call surface plasmons. The field enhancement is so strong that it enables detection of single molecules and can even drive optical transitions that are normally forbidden by quantum mechanical selection rules. To understand hotspots, we first need to understand surface plasmons. Let me give you an analogy. Imagine a crowd doing the wave at a stadium. Individual people stand up and sit down in coordination, creating a traveling wave pattern. This is similar to how electrons behave in a metal. Here we have a metallic nanoparticle represented by this gold circle. The blue dots are conduction electrons. When light hits the particle, it drives these electrons to oscillate collectively, creating a localized surface plasmon. When the frequency of incident light matches the natural oscillation frequency of the electrons, we get localized surface plasmon resonance, or LSPR. The resonance frequency omega LSPR equals the bulk plasma frequency omega p times the square root of 1 over the sum of the metal permittivity epsilon m plus 2 times the dielectric permittivity epsilon d. This resonance frequency depends critically on the nanoparticle size, shape, and the dielectric properties of the surrounding medium. For noble metals like gold and silver, the resonance typically occurs in the visible region of the spectrum, which is why gold nanoparticles appear red or purple in solution. Now let's understand the physics behind the enormous field enhancement. Why do these hotspots occur? The key concept here is the lightning rod effect. Just as a lightning rod concentrates electric field at its sharp tip, nanoscale features concentrate electromagnetic fields. Here is an ellipsoidal nanoparticle with a sharp protrusion. The field lines concentrate at the sharp tip, creating a hotspot where the field intensity is maximum. The field enhancement factor scales inversely with the radius of curvature. Sharper features produce stronger enhancements. The intensity enhancement at the tip is proportional to 1 over r squared, where r is the radius of curvature of the tip. Now we come to the most powerful type of hotspot, nanoscale gaps between metallic nanostructures. This is where the magic really happens. Let me ask you a question. Why are the gaps between nanoparticles more special than isolated particles? The answer is that when two nanoparticles are brought close together, their individual plasmon modes couple, creating a new hybridized mode that confines the field to the gap region. Here we have a dimer, two gold nanoparticles separated by a nanoscale gap. The intense purple field in the gap represents the hotspot where field enhancement reaches its maximum. Experimental measurements show that gap hotspots can exhibit enhancement factors from 1 million to 10 billion, depending on the gap size. The fourth power of the field enhancement in the gap scales approximately as 1 over d to the 10th power, where d is the gap distance. This explains the extreme sensitivity to gap size. For Raman scattering, which we'll discuss shortly, the intensity enhancement scales with the fourth power of the electric field, making these hotspots incredibly powerful. The size of the gap is critically important. Let's examine how field enhancement depends on gap distance. For a 1 nanometer gap, the enhancement factor can reach about 100 million. Increasing the gap to 5 nanometers reduces the enhancement to about 1 million. At 20 nanometers, the enhancement factor drops to around 10,000. This extreme distance dependence is both a challenge and an opportunity. It enables unprecedented nanoscale spatial resolution in spectroscopy. Now let's discuss one of the most important applications of plasmonic hotspots, surface-enhanced Raman scattering, or SERS. First, let me explain Raman scattering. When light interacts with a molecule, most photons scatter elastically. However, a small fraction scatter inelastically, exchanging energy with molecular vibrations. Normal Raman scattering is extremely weak. Typically, only 1 photon in 100 million undergoes Raman scattering. This makes detection challenging. In SERS, a molecule positioned in the hotspot between two nanoparticles experiences enormous field enhancement. The laser light is enhanced, exciting the molecule more strongly, and the Raman scattered light is also enhanced. SERS provides total enhancement factors ranging from 1 million to 100 trillion, enabling single-molecule detection. The SERS enhancement factor equals the product of the local field enhancement at the laser frequency omega L squared times the local field enhancement at the Raman frequency omega R squared. This is called the electromagnetic enhancement mechanism, and it is the dominant contribution to SERS for most systems. There is also a secondary mechanism called chemical enhancement, which contributes additional enhancement. Chemical enhancement arises from charge transfer interactions between the metal surface and the adsorbed molecule. This modifies the molecular polarizability. Chemical enhancement typically provides factors of 10 to 100, which is much smaller than electromagnetic enhancement, but still important for certain molecules. The total SERS enhancement is the product of both electromagnetic and chemical enhancement mechanisms working together. Now let's explore a fascinating phenomenon: how plasmonic hotspots can enable apparently forbidden optical transitions. Let me ask another question. What makes an optical transition forbidden in the first place? The answer lies in quantum mechanical selection rules. In the electric dipole approximation, transitions must satisfy specific rules based on angular momentum and parity. For electric dipole transitions, the angular momentum quantum number L must change by plus or minus 1, and the magnetic quantum number m can change by 0, plus 1, or minus 1. Transitions that violate these selection rules are called forbidden transitions. They can still occur through higher-order processes like magnetic dipole or electric quadrupole, but they are much weaker. So how do plasmonic hotspots enable these forbidden transitions? First, the enormous field intensity in hotspots can simply overcome the weak transition rates of forbidden processes. Even a weakly allowed transition becomes observable with million-fold field enhancement. Second, the extreme field gradients in nanoscale hotspots break the electric dipole approximation. The field varies significantly over molecular dimensions, enabling magnetic dipole and electric quadrupole transitions. The field gradient can reach values of approximately E maximum over D, which is around 10 to the 10th volts per meter squared for a 1 nanometer gap. Experimentally, researchers have observed multiple forbidden transitions in molecules placed in plasmonic hotspots, including spin-forbidden transitions and symmetry-forbidden transitions. Now let's discuss practical design principles for creating optimal plasmonic hotspots. First, use noble metals like gold and silver for visible and near-infrared applications. These metals have low losses and strong plasmonic responses in this spectral range. Second, create sharp features or small gaps. The smaller the radius of curvature or gap size, the stronger the field enhancement. Third, match the plasmon resonance frequency to your excitation wavelength by tuning the nanostructure geometry and composition. Here are 3 common geometries: spheroids with controlled aspect ratio, nanostars with multiple sharp tips, and dimers with nanoscale gaps. Each has advantages for specific applications. Despite their tremendous potential, engineering plasmonic hotspots faces several challenges. Challenge 1 is reproducibility. Creating identical hotspots across large areas is difficult because field enhancement is extremely sensitive to nanometer scale variations in geometry. Challenge 2 is heat generation. Strong optical absorption in metals leads to local heating, which can damage molecules or reshape the nanostructures themselves. Challenge 3 is positioning molecules precisely in the hotspot. The enhancement region is typically just a few nanometers, requiring sophisticated chemistry to place molecules correctly. Challenge 4 is spectral bandwidth. Plasmonic resonances have finite bandwidth, limiting the spectral range over which strong enhancement occurs. Let me highlight some recent advances and exciting applications of plasmonic hotspots. One major application is single-molecule detection and sequencing. SERS hotspots enable identification of individual molecules by their vibrational fingerprints, with applications in DNA sequencing and protein analysis. Another exciting area is plasmon-driven chemistry. The intense fields in hotspots can drive chemical reactions by exciting molecular vibrations or generating hot electrons that participate in redox reactions. Hotspots also enable ultra-fast spectroscopy with nanoscale spatial resolution, revealing dynamics of energy transfer and chemical reactions at molecular length scales. In the quantum regime, extremely small hotspots can reach the strong coupling limit, where molecules and plasmons hybridize to form new quantum states called plexitons. Let's discuss when we need quantum mechanics versus when classical electromagnetism suffices. For gaps larger than approximately 1 nanometer, classical Maxwell equations provide accurate descriptions of plasmonic hotspots. Below 1 nanometer, quantum mechanical effects become important. Electrons can tunnel across the gap, screening the field and reducing enhancement. The quantum regime typically begins around 0.3 to 0.5 nanometers, where electron tunneling becomes significant. Quantum effects actually limit the maximum achievable field enhancement. As the gap shrinks, quantum tunneling prevents the field from growing indefinitely. How do we actually measure these hotspots experimentally? This is challenging because the regions are so small. Technique 1 uses SCRS with molecular probes. By monitoring Raman signals from molecules, we can infer the local field enhancement. Technique 2 is scanning near-field optical microscopy, or SNOM. A sharp metal tip scans across the surface, mapping the local field with nanometer resolution. Technique 3 uses electron energy loss spectroscopy in a transmission electron microscope. Electrons probe the local density of electromagnetic states with sub-nanometer resolution. Technique 4 maps fluorescence enhancement from quantum emitters positioned near the nanostructures, providing indirect information about field distributions. Computational modeling is essential for understanding and optimizing plasmonic hotspots. The finite element method divides space into small elements and solves Maxwell equations numerically. It handles complex geometries well, but can be computationally expensive. Finite difference time domain methods discretize both space and time, directly solving Maxwell equations in the time domain. They are efficient for broadband calculations. The boundary element method only discretizes metal surfaces, rather than all space, making it very efficient for metallic nanostructures. All these methods solve Faraday's law, the curl of E equals minus partial B partial T, and Ampere's law, the curl of H equals partial D partial T plus the current density J. Let me conclude by discussing future directions and open questions in this field. One exciting question is whether we can achieve single photon nonlinearities using plasmonic hotspots. This would enable quantum information processing with light at the nanoscale. Another important challenge is developing methods to stabilize hotspots for practical devices. Current structures often degrade under intense illumination. Extending hotspots to other spectral regions like mid-infrared or ultraviolet requires new materials beyond gold and silver. This is an active area of research. Finally, what is the fundamental limit of field confinement? Quantum mechanics and non-local effects will ultimately limit how small we can squeeze light. Let me summarize the key concepts we've covered in this lecture. First, plasmonic hotspots arise from localized surface plasmon resonances in metallic nanostructures, where collective electron oscillations concentrate electromagnetic fields. Second, nanoscale gaps between nanoparticles provide the strongest field enhancement due to coupled plasmon modes and extreme field confinement. Third, surface-enhanced Raman scattering exploits hotspots to detect single molecules by enhancing both excitation and emission processes. Fourth, apparently forbidden optical transitions can be enabled by the enormous field intensities and gradients in hotspots. Finally, applications of plasmonic hotspots span diverse fields, including analytical chemistry, molecular biology, catalysis, and quantum optics. Thank you for your attention. The field of plasmonics and hotspot engineering continues to evolve rapidly, offering exciting opportunities for both fundamental research and practical applications.